Okay, yeah, sorry for the delay. I'm Lohit, and now I'm going to present the stochastic process module in UQpy. So the stochastic process module primarily contains classes and functions for generation of stochastic process from power spectrum, bispectrum, and autocorrelation function, as well as modules to translate these generated stochastic process to some other non-Gaussian stochastic process maybe. Uh, so the stochastic process module can be imported from this command from UQpy import stochastic process, as we have seen throughout these 2 days. The presentation is primarily divided into 2 parts. The first part covers spectral representation method, bispectral representation method, and Carhon and Levy expansion. So these 3 methods deal with generation of stochastic process from said power spectrum, bispectrum, and autocorrelation functions. The second part is translation process and inverse translation process. These 2 deal with translating the generated Gaussian stochastic processes into non-Gaussian stochastic processes. So let's dive in. First, we'll go to the spectral representation method. The spectral representation method is a sum of cosines formula for the generation of stationary stochastic processes with the prescribed power spectrum. The formula is given here, and the details can be found in the paper Shinozuka-Diodatis simulation of stochastic processes by spectral representation. The class attributes are given here. The first one is n samples. So this is an integer which indicates the number of samples to be generated. S is an n-dimensional array of the power spectrum. So we are primarily going to concentrate on generation of one-dimensional univariate stochastic processes. So for that, the shape of the power spectrum is of 1, NW, and dt is the length of the discretization in time domain, dw is the length of discretization in frequency domain, and t is the number of discretizations in time, and w is the number of frequency discretizations. And the last one, case, this is a string. It has 2 optional values, uni and multi. So uni refers to univariate stochastic processes, and multi denotes the generation of multivariate stochastic processes. The class SRM has one output attribute, samples. It's an n-dimensional array, and in the case of univariate samples, the shape is n samples, nt. As we have seen throughout, as class from a module can be imported in one of the 2 ways. The first way is from UQpy import stochastic processes, and then subsequently x is equal to stochastic process.srm, or directly import the class itself first with from UQpy.stochasticProcess import srm, and then use it. So the last line here, samples is equal to x.samples. So this is just to extract the output attribute from the class. So there are 4 examples which can be found in UQpy example stochastic process. So these 4 cases denote 4 different permutations of SRM. So the first case is one-dimensional univariate stochastic processes. The second one is one-dimensional multivariate stochastic processes. The third one is n-dimensional univariate stochastic processes. And the last one, the most general, the n-dimensional multivariate stochastic processes. A point to note is that we use the fast Fourier transform implementation for the simulations, which exponentially increases the computational efficiency of the algorithm, details of which can again be found in Shinozuka and Diodatis paper and subsequent papers written by them developing the whole thing. Now we go on to seeing an example Python notebook in the first case. That's the one-dimensional univariate case. Yeah, this is the notebook for spectral representation method, one-dimensional univariate case. So here we see that we first import the class using this command, and then we have a bunch of input parameters that are necessary for the generation. The first one is number of samples, then the number of dimensions, number of variables, the number of discretizations, and the length of discretization across different domains. And this line 3 condition is just a condition we need to check to prevent aliasing in the case of fast Fourier transform, and details of which can again be found in the paper. Then we define the power spectrum density function. It could be any analytical function or anything really. So we have this function. Then we first define an SRM object using the parameters and the class. Then we extract the samples out of the object using this command. And now we have samples of the shape and samples comma NT. Here is the one sample realization of a sample generated from the spectral representation method. So here on the x-axis, we have the time domain, and on the y-axis, it's the different values. At the bottom, we can see that these samples are in fact of mean 0. We see the first line, it's like nearly 0. And we can also check the variance of the samples generated using the second one. It's just the area under the power spectral density function, and that matches as well. So yeah, that's it for this example. Yeah. Next, we go to the BSRM class. BSRM stands for bispectral representation method. So this method provides the simulation formula for simulation of stationary stochastic processes from a prescribed power spectrum as well as a bispectrum. So this is the simulation formula given here. Point to note is that here S underscore P is the pure part of the power spectrum, and B underscore P, omega I, omega J are the partial bicoherences values, which are derived from the bispectrum. So this part primarily contains the information from the bispectrum, details of which can be found in the paper Shields Chem simulation of higher order stochastic processes by spectral representation. Yeah. The BSRM class has the following input attributes and samples S, B, DT, D omega, and T, and NW actually, yeah. So the sample the input attributes are similar to the spectral representation method, only the B parameter is added, which is an n-dimensional array which contains the information about the bispectrum of the shape NW, NW. And the output attribute from this class again is samples, which is an n-dimensional array of the shape n samples, NT. So as we have seen over and over, the BSRM class can be imported in two ways, and this information about the samples is contained in this output attribute samples. And there are two examples which can be found in the GitHub repository. First one is BSRM 1D, the second one is BSRM ND. The first one is for one-dimensional samples, and the second one is for n-dimensional samples. Again, BSRM is also implemented in fast Fourier transform, so it's computationally very efficient. And let's go and see the first example, BSRM underscore 1D. So again, we import the BSRM class from UQpy stochastic process, and we define similar attributes. First one is number of samples, second one is number of dimensions, NT and W, DT, and DW. We define a power spectrum again, and this is the new part in which we define the bispectrum. So a bispectrum typically has a real part as well as an imaginary part. In this case, we assume that the real part and the imaginary part of the bispectrum are same, and this part initializes the two-dimensional bispectrum, and then subsequently, yeah, line 25, here we initialize a BSRM object using the different parameters we have defined above, and we extract the samples from the BSRM object using the second command. One such sample which is generated by a BSRM is shown here. So again, the x-axis is the time domain, and the y-axis shows the values of the process as such. Again, we see that the mean of the samples is nearly 0, and the variance matches the variance which is defined by the power spectrum. And the third component which shows the skewness is also the same as the skewness, which should have been because of the bispectrum. And yeah, the samples generated by BSRM are skewed because of the presence of a bispectrum. Okay, so next we go on to Carhoon and Lavey. Yeah, next is the KLE class. It's the Carhoon and Lavey expansion formula for simulation of stochastic processes from autocorrelation function rather than a power spectrum. So the methods we have seen so far, SRM and BSRM, deal with information in the frequency domain rather than the time domain, but KLE uses the information contained in the time domain for the generation of samples. So this is the formula for the generation using KLE, where lambda I is the ith eigenvalue and omega I are the ith eigenfunction of the autocorrelation function R. The input attributes of KLE class are just 2 n-samples and R. N-samples again is the number of samples, and R is an array of the 2-point correlation function which is of the shape nt, nt. The KLE is a really simple and elegant class for generation of stochastic process in the time domain. The output attribute is samples, which is again of the shape n-samples, nt. Again, KLE can be imported in 2 ways, similar to SRM and BSRM, and the samples can be extracted from the output attributes. We have an example illustrating the use of KLE. Switch to that. Yeah, Carhoon and Lavey expansion. Now, in line 1, we have imported KLE from UQpy stochastic process. And then we define the number of samples to be generated. And next we define the target autocorrelation function, which we want to generate from. And then we have the KLE object, which is just KLE and simulations, R. And we extract the samples from the KLE object dot samples. And the plot of one such realization is given in here, where the x-axis is the time domain and the y-axis is the values. And we can even do this statistical checks for the simulation, where the mean is 0 and the variance is 2. So this is for the Carhoon and Lavey expansion. And yeah, next we switch gears and talk about translating a Gaussian process, a Gaussian stochastic process into non-Gaussian stochastic process, and inverse translating a non-Gaussian stochastic process back into the Gaussian domain. So first we talk about the forward translation. So here is the theory for the translation process. So assume that GT is a Gaussian stochastic process with 0 mean and standard deviation sigma, and autocorrelation function R underscore G tau. So this can be translated into a non-Gaussian sample, which has a marginal cumulative distribution function F underscore NGX through the simple nonlinear transformation. So this is akin to the inverse transform as such. So yeah. But following this forward translation process distorts the correlation function of the Gaussian samples. The distorted correlation function of the non-Gaussian stochastic processes can be computed using this integral, and details of all this is provided in Grigori simulation of stationary non-Gaussian translation processes. Next, we go on to the definition of the translation class input attributes. The first one is samples G. So it's an n-dimensional array containing the Gaussian samples. Next is a marginal, which is a list. This defines the names of the marginal distribution into which we want to map to. And params shows the list of distribution parameters of the defined distributions. So these two parameters should be akin to the UQpy distributions model, which was discussed yesterday by Dimitris. And dt, d omega, and t and omega are similar to the definitions we have followed throughout. And S underscore G and R underscore G. So S underscore G is the Gaussian power spectrum, and R underscore G is the Gaussian autocorrelation function. we need to provide only one of these. We can either use the power spectrum or the autocorrelation function, and the method works. And the output um, attributes are given here. The first one is samples underscore ng, which is the array of non-Gaussian samples which have been translated from the Gaussian to non-Gaussian distribution. And s underscore ng is the distorted power spectrum, and r underscore ng is the distorted autocorrelation function. Yeah, here is how we need to import the translation process, two ways again. And below we have two cases of the translation process. You can note that in the first one, we just input the Gaussian power spectrum, and we don't need to provide anything for the Gaussian autocorrelation function. In the second one, we don't provide any power spectrum, but we give Gaussian autocorrelation function as input. And this line shows all the output attributes from the translation class. So the first one would be non-Gaussian samples, then it's a non-Gaussian autocorrelation function, and S is a non-Gaussian power spectrum. So we can get all these outputs from the translation class. We do have an example for the translation class as well. Yeah, translation. So here we import two functions here, two classes, two modules here. First one is translation, and the second one is SRM. First, we generate Gaussian stochastic processes using the spectral representation method, as we have seen before. And next, yeah, this part. We translate the generated Gaussian processes into a uniform distribution with parameters 0 and 1. So here, the first one is samples, then the marginal, then the parameters of the marginal, and then the details about the discretizations. And we use the Gaussian autocorrelation function input. And after running this, we get the non-Gaussian samples and non-Gaussian autocorrelation function. We can see in this plot the two autocorrelation functions. The blue one is the Gaussian, and green one is uniform. Since the variance of uniform distribution 0 to 1 is like 1 by 12, which is 0.08, we see that the variance has been decreased from 1 to around 0.1. Yeah, this is how to use the translation class. Next, we move on to the inverse translation class. Yeah, the inverse translation. So point to note here is that the inverse of the above described forward translation might not always be possible. So the correlation distortion doesn't always allow you to find inverse correlation in the Gaussian realm, which, you know, after translation gives the required non-Gaussian correlation. So we need to be mindful about these incompatible cases when we are trying to map them back. And another point to note is that the closed form solution for inverse translation cases do not exist as such. So iterative methods to find the underlying Gaussian autocorrelation function are popular. And flowchart detailing the iterative method for estimating the underlying Gaussian autocorrelation function is given in the next slide. The details can be found in the paper Shields, Dioratis, and Bocchini, a simple and efficient methodology to approximate a general non-Gaussian stationary stochastic process by translation process. And yeah, here is the flowchart. So it's a simple flowchart, but quite powerful. First, we start with initial guess for the what the Gaussian power spectrum might be, and we compute a Gaussian autocorrelation function using the Wiener-Kinchen transform, and then using the Nahtaf transform, which I've seen in here, you compute the translated non-Gaussian autocorrelation function, and then we convert it back into a non-Gaussian parse spectral density function using the Wiener-Khinchin transform again, and we see how different we compute error matrix of the target non-Gaussian parse spectral density function, and based on iterative conditions or convergence conditions, we determine if the iterations have been finished or not. And if they haven't been finished, we have an upgradation scheme for the next initial value, and the loop continues. And if we determine that the convergence has been reached, and we end the loop. And the inverse translation class input attributes have been given here. They more or less mirror the input attributes from the translation class. Here, the first parameter samples ng is changed from samples g, which reflects the change from Gaussian samples to non-Gaussian samples. And the last two parameters, s underscore ng, r underscore ng, here denote the power spectrum and the autocorrelation function of the non-Gaussian samples. The output attributes again mirror the translation class output attributes. Here, the first output attribute is samples underscore g. The second and third are s underscore g and r underscore g, which denote the power spectrum of the underlying Gaussian samples and the autocorrelation function. Similar to the translation class, there are two ways to use inverse translation. In the first case, we see that we just pass the non-Gaussian power spectrum, and we don't need to pass any information regarding the non-Gaussian autocorrelation function. And in the second case, it's the reverse. Yeah, and the output attributes are shown here. First one is the Gaussian samples, the second one is Gaussian autocorrelation function, and the third one is Gaussian power spectrum. There is an example illustrating the inverse translation class, and let's discuss that. Yeah. So here, well, the sequence of this example is going to be, first we generate some Gaussian stochastic processes using SRM class again, and we translate the said the generated Gaussian stochastic processes into a uniform distribution and translate them back from uniform to Gaussian. So as seen before, this part is for the generation of Gaussian samples using SRM method. And here we translate the samples again from Gaussian to uniform distribution. We see that the correlation function is distorted. Next, we inverse translate the generated non-Gaussian samples. So here we pass the non-Gaussian samples, the marginal of the non-Gaussian samples, and the parameters and the different discretization data, and the autocorrelation function of the non-Gaussian samples. And we just extract the output attributes from the object. So here we see that the extracted Gaussian autocorrelation function r underscore g matches the original autocorrelation function from here. Yeah, you can. Okay. Oh yeah, so R actually represents the original autocorrelation function before like start doing even translation. So we can see that it's a very close match between them both. We just see some differences here, but we can see that after inverse translation, it actually shows the original autocorrelation function. So this wraps up the inverse translation process as such, and the stochastic processes as a whole. And as always, any input regarding future development of stochastic process module is always welcome. And now I turn back to Professor Shields. Yeah, that's it. Have a good day.
Thank you, everyone. This concludes the UQpy training session. I want to end with a few notes. The first and most important note is that I want to thank the UQpy team and everyone who presented today. That includes, in no particular order, Dimitris Giovannis, Audrey Olivier, Mohit Chauhan, Akash Bangalore Satish, and Lohit Vandanapu. Their hard work really made all of this possible, and this was quite an undertaking, and we certainly appreciate their efforts. So on that note, I also want to remind everyone that we have the forum set up, uqpy.freeforums.net, for you to provide us with any feedback related to the training session itself, or related to the software, its capabilities, what you would like to see built in the future, as well as what you're using as it is. Moreover, the UQpy is not perfect. We acknowledge that there are some limitations and perhaps some bugs in there. So if you see something, please let us know so we can fix it and so we can improve the code. And on that note, I want to encourage everyone to play around with it. Get in there, investigate, see what you can do with it, link it to your models, and have fun with it. And then as you're doing that, give us feedback. We're very excited to hear what people think of the software and see how we can make it better and make it a widely used tool for anyone who's interested in uncertainty quantification and the vast array of applications that are out there. So on that note, I will conclude. And again, I thank all the speakers, and I thank the participants for sticking with us for 2 days. And thank you again.